Hello students, welcome back to another video of metric spaces. Today we will discuss the new chapter. We will start the new chapter, continuous functions. So next chapter is continuous functions. Third chapter of the metric space, continuous function. This is the smallest chapter in this whole syllabus. First of all, in this chapter there is only one point, definition of continuous function, and some examples on that. So the definition of continuous function. Definition of continuous function. Now we are dealing in metric spaces. So here the function is from one metric space to another metric space. So let xd and suppose some y rho is function defined on the metric space. So let xd and y rho be metric spaces, and let f from function f from x to y be function, just a second, f from x to y be a function f from x to y be a function, then this function f is said to be continuous. Then f is said to be continuous. F is said to be continuous function at some x belongs to x. Function f is said to be continuous at any element at some x belongs to x if there exists a sequence suppose sequence xn in x. If there exists sequence xn in x such that sequence xn converges to x, then that is the sequence in x which converges to x belongs to x, then the image of this sequence, that is image of this sequence under f means f of xn converges to the image of this element, that is f of x. Then f of xn converges to f of x, and these f of xn and f of x are the elements of y. So f of xn converges to f of x in y. Function f is said to be continuous from metric space x to metric space y if there exists a sequence xn in x which converges to x in that x, then the image of that xn, there exists a sequence xn, so image of this xn must converges to image of this element. If this xn converges to x, then image of this xn must converge to image of this x in y. Then we say that given function f is continuous function. So here xn converges to x, yn converges to y, and we know that the convergence of sequence in this previous chapter, convergence means for epsilon positive there exists delta positive such that distance between these two is less than epsilon. Similarly, distance between these two is less than epsilon. So these are the definition of convergence. Now we will solve some examples. So first numerical is show that this is the definition of continuous function, means function f is said to be continuous if the image of sequence in xn which converges to x in x, image of that sequence f of xn converges to f of x in y. Now show that any constant map from a metric space to another, that is one metric space to another metric space, is continuous. Show that any constant map from a metric space to another is continuous. So here x and y, suppose two metric spaces and f from x to y be a function, we have to such that that function is constant function, that is f of x is equals to some c for all x belongs to the domain. This is the definition of constant function. We have to show that that constant function is continuous function. Let x and y be two matrix spaces and f from, this is small f from x to y, be a constant function, be a constant map. That is, this constant function means f of x is equals to some constant c for all x belongs to x. For every element of x, the image of that element is some c. So this is the definition of constant function. So we have to prove that this function is continuous function. For that we have to prove that suppose some xn is sequence in x which converges to some element in that x. So let xn be a sequence in x, xn be a sequence in x such that xn converges to x, in x. Now we have to show that image of this xn converges to image of this x. That is, to show that f of xn converges to f of x in y, since given function is constant function. So image of xn will be again c for every xn, also image of x will be again c, so that c, f of xn and f of x both have same images. So since given function f is constant, therefore f of xn will be c for every element of that sequence, image of that element is c, also image of x will be c, f of x is also c. So distance between these two, so the distance between f of xn and f of x is equals to distance between these 2 points, that is distance between c and c. C is the only point, so distance between c and c is equals to 0. This implies that distance between f of xn and f of x is equals to 0, which is less than any epsilon positive. For every epsilon positive, this distance is less than that epsilon. Therefore we can say that this f of xn converges to f of x. Therefore by definition of convergence, we can write this f of xn converges to f of x in y. Hence the given function is continuous. Hence f is continuous function. So to prove any function is continuous, we just have to prove that we have to take one sequence in domain which convergent sequence in domain, that is some sequence xn in x which converges to some element x in x, and we have to prove that image of that sequence, that is image of this xn, image of xn is f of xn converges to image of this x, that is f of xn converges to f of x. Then we will say that the given function is continuous function. So the next example, similar example, that is for your homework, is show that, this is for your homework. Next example, show that identity map from a matrix space to another is continuous. From a matrix space to itself, identity map from matrix space to itself, that is x to x, f from x to x via identity map. Identity map means f of x is equals to x, is continuous. continuous. This is for your homework. Just function f from x to x and defined as f of x is equals to x. So we have to take one convergent sequence in domain, that is in x, such that xn that converges to x, then we have to prove that f of xn converges to f of x. So f of xn will be xn and f of x will be x. As xn converges to x, we can clearly say that f of xn converges to f of x, because the f of xn will be xn, because the function is identity map. Identity map means f of x is equals to x. So f of xn is equals to xn, f of x is equals to x, then that xn converges to x, so f of xn converges to f of x. So this is the solution of this example, that is for your homework. Now the next example is show that the map from R square to R, show that the map from R square to R given by alpha of, that is there are two functions, alpha from R square to R, suppose, then mu from R square to R. So first function alpha of, now the elements of R square are order pair. So alpha of x y is equals to x plus y and mu of x y is equals to x into y. So we have to show that these two functions both are continuous. These functions are continuous. Show that the maps from R square to R given by first function alpha of x y is equals to x plus y and mu of x y is equals to x into y are continuous functions. So here the solution, first of all we will prove this is continuous map alpha from R square to R such that alpha of x y is equals to x plus y. Claim is alpha is continuous. To prove any function is continuous, we will just take one sequence in domain, one convergent sequence in domain. Now here the domain is R square, so sequence in R square is of the form order pair, that is xn yn. So let this xn yn be a sequence, be a convergent sequence. So we will prove, take this be a sequence in R square such that this sequence converges to some element in that R square, such that this xn yn converges to order pair xy, the sequence in R square, so that converges to some element in R square, and the elements in R square are of the form order pair. So xn yn converges to xy in R square. Now xn yn converges to xy in R square means this xn converges to x and yn converges to y in R. This is we have seen in the convergence of a product metric space in the previous chapter. So clearly this xn converges to x in R and yn converges to y in R. Xn converges to x in R, yn converges to y in R. To show that, we have to show that image of this xn yn converges to image of this xy. To show that image of this sequence under the given map alpha, that is alpha of xn yn converges to alpha of xy, that is to show that alpha of xn yn means the function alpha is defined as alpha of xy is equals to x plus y. That is we have to show that this xn plus yn function is defined as addition of these two, it converges to x plus y. Now we have xn converges to x and yn converges to y, so their addition xn plus yn converges to x plus y. So as xn converges to x and yn converges to y in R, therefore we can write their addition xn plus yn converges to x plus y in R. So this xn plus yn is the image of alpha of x and yn. Thus, sorry, thus this is the image of alpha of xn yn, which converges to image of xy. Hence, the given function alpha is continuous map. Therefore, alpha is continuous. Alpha is continuous. Now, similarly, we will take this mu from r square to r defined by mu of xy is equals to x into y, and we have to prove that this mu is also continuous map. So, let the function mu from r square to r defined as mu of xy is equals to x into y. To show that mu is, our claim is, this mu is continuous function. Continuous function. So, to show this function is continuous, we will take one sequence in r square which converges to some element in r square. So, let xn yn be sequence in r square. Let xn yn be sequence in r square such that that sequence xn yn converges to xy in r square. Now, xn yn converges to xy in r square. So, therefore, by theorem on product metric space, we can write this xn converges to x in r and yn converges to y in r. Now, we have to show that mu of xn yn converges to mu of xy. To show that mu of xn yn converges to mu of xy, that is, we have to show that mu of xn yn defined as xn into yn. So, this xn into yn converges to x into y. Now, we have this xn converges to x, yn converges to y. So, xn into yn converges to x into y in R, as xn converges to x and yn converges to y in R implies their multiplication. Xn into yn converges to x into y in R. These results you have seen in the real analysis. This is in real, that is, this xn is and yn both are sequences in R and they are convergent sequences. So, their addition and their multiplication converges. So, xn into yn converges to xy in R. So, this is the image of mu of x and yn, and this is the image of mu of xy. So, this implies mu of xn yn converges to mu of xy in R. Hence, the given function mu is continuous function. Given function mu is continuous function. So, this is the solution of given example. Now, one remark is that you can prove similar like this example. Here we have seen functions from r square to r is continuous function. So, we can generalize this result, r raised to n to r is also continuous function, and this mapping r raised to n to r is called projection map. The projection map, suppose Pi from r raised to n to r is, suppose this projection map which is given by projection map r raised to r to n, sorry, r raised to n to r given by Pi of x is equals to xi, Pi of x is equals to xi, where this x is n tuple element, where where x is equals to x1 x2 up to xn. Function is applied on these elements of this domain, and the elements of this domain are n tuple elements. So this function is defined as pi of x is equals to xi. That is, suppose this is r cube, then the function p is applied on 3 tuple element, then this function is defined as, suppose p1 of x is equals to x1, p2 of x is equals to x2. So this function is defined in this manner, and this function is given by this is continuous. If you have to prove this in the exam, then the function is given by pi of x is equals to xi. You have to consider one convergent sequence in r raised to n. Suppose xn be a sequence in r raised to n that converges to xn. The elements of xn are of the form this, that is, the elements of xn are n tuple elements, and that suppose this sequence xn, x1 x2 up to xn. Suppose we will denote that sequence. So if you want to prove, there is no need to prove, but if you want to prove this result, then suppose sequence xn in this r raised to n of this form, suppose x1 x2 up to xn. Suppose this is the notation for nth. Suppose this is notation for that sequence x1 x2, n tuple elements, but this is n denotes for the xn. This is the element, these are the elements of sequence xn. So this sequence, suppose this sequence converges to x is x1 x2 up to xn, x1 up to xn. Suppose this sequence xn converges to x. Now this sequence xn converges to x means this first element converges to this first element, this x2 raised to n converges to x2, similarly xn raised to n converges to xn. So this is by using the definition of product metric space. So this implies this x1 raised to n converges to x1 in R. This is in R raised to n, this is in. So these elements are real numbers, this also a real number, this also real number. So this implies x1 raised to n converges to x1, x2 raised to converges to x2 in R. This is again in R. Similarly, x raised to nth element of this sequence again converges to xn in R. So function is defined as pi of x is equals to xi, and we have to prove that image of this sequence converges to this element. So if we apply the function on this xn, then pi of xn, the pi of xn means the function is applied as pi of xn means xi to the power n. Here pi of xn is equals to xi to the power n. So xi to the power n converges to xi. Since this x1 to the power n converges to x1, x2 to the power n converges to x2, xn to the power n converges to xn, implies pi of xn, that is pi of xn is xi raised to n. So that xi raised to n. So every element is converges to itself. So if we apply p, then every element of that sequence converges to, that is image of sequence converges to these elements. So that is we will just continue this proof. Pi of xn is equals to xi. Function is defined as pi of xi is equals to, pi of x is equals to xi. So pi of x raised to n, notations of this sequence xn are xi raised to n. So this pi of xn will be x raised to n, but clearly from these lines we can say that xi to the power n converges to xi, because if we put I is equals to 1, then x1 to the power n converges to x1, x2 to the power n converges to x2c. So pi of xn converges to xi raised to n. So this is that is, and this xi to the power n converges to xi in R. Image of this is this, and this converges to xi, and that is we have to prove that image of this converges to some element in codomain. So codomain is R. So this xi raised to n converges to xi in R implies pi of xn converges to pi of x in R. Hence this is the solution of projection map. There is no need to prove this result. This is just for your remark, that is, if you, this question can be asked for multiple acts as a multiple choice question in the if the exam holds online. So, this for that concern this projection map is also continuous function. So, we will see some examples in next lecture.